All right. Good afternoon. Just looking at once again domain and asymptotes, and now we started out looking at domain and vertical asymptotes, and we left off with some of the fundamentals regarding whether or not the rational function is going to consist of horizontal or slant asymptotes, and again we have for rational function. And again, we have r of x equal to a fraction where we have a ratio of polynomials, where we have the top polynomial, is going to be of degree n, and the denominator is going to be of degree m. And in terms of the degree comparisons, again, if the degree of the numerator is less than that of the denominator, then there's going to be a horizontal asymptote y is equal to 0. So y equals 0 is going to be the x-axis. And if we have that n is equal to m, then we're going to have a non-negligible horizontal asymptote where we have that y is equal to a of n over b of m, and this will be a constant resulting from taking the ratio of the highest order terms. And if we have that n turns out to be greater than m by 1 degree, we're going to have a slant asymptote, and this is going to be a line that's going to run diagonally, and it's going to be represented by the slope-intercept equation, which I happen to have in the form of y is equal to alpha x plus beta. And the reason I have those letters is that I've already used up the letters m and b. Otherwise, if I did not, I would have y is equal to mx plus b. And once again, if the numerator is greater than the degree of the denominator by more than 1, you're not going to have any horizontal or slant asymptotes. Now, just taking a case of what we have regarding domain and asymptotes. And let's say that if we have, for instance, if we're looking for the domain and the asymptotes, and we'll say you have of the function. So we will have the r of x is going to be equal to, so we can say we have x cubed plus 3x squared plus 4x plus 1 all over x squared plus 1. Okay, so we have for this particular rational function, if we're looking at the domain, again, for fractions, the denominator cannot be equal to 0. So starting out, so we have the x squared plus 1 cannot be 0. And here we have the sum of squares. Now, in terms of real integer coefficients, while you can factor a difference of squares, we cannot factor a sum of squares. So I can isolate the x squared if I move the 1 over upon subtracting. So I have x squared cannot be equal to -1. And if I perform the principal square root rule reduction, or I should say the square root property of equality reduction, so we have x squared going to x, we have cannot be equal to plus or minus the square root of -1. And it's going to turn out that for the excluded values, both of these are going to be complex numbers. But in terms of what we have regarding domain and asymptotes, we're concerned with the real number system. And if you notice, both of these numbers excluded from the domain, they're not even from the real number system. And so we have, there are no real values excluded. or no real values x excluded. So for what this is going to mean will be at least a couple of things here. So there are no real values x excluded. So that means that x can be any real value. X can be 0, and it can be any real positive, and it can also be any real negative. Okay, so we have for the domain, this function is going to have the set of all real numbers. And once again, the interval notation for the set of all real numbers, we have parentheses around negative and positive infinity. And also, since no real values are excluded, okay, so there are no restricted values, okay, and if we did have those, there was the potential for those restricted values to define, okay, vertical asymptotes. But since there are no real values x excluded, okay, again, there's going to be no vertical asymptotes. All right, so if we have any asymptotes for this function, it is not going to be in the existence of vertical asymptotes. Now, in terms of whether we have any kind of asymptote, okay, and the categories, okay, we have either horizontal or slant asymptotes. And just looking at what we have here, is going to come down to the comparison of the degrees existing in the numerator and denominator. So for what we have in the case of the numerator, okay, the highest degree term is x to the third. So the degree of the numerator n is equal to 3. And for what we have in the denominator, okay, the higher degree term, we have x squared. Okay, so we have the m is equal to 2. So we have n at 3, m at 2. So again, so first case does not apply since 3 is not less than 2. 3 does not equal to 2, so the second case does not apply. But we do have that 3 is greater than 2, and the difference is going to be 1. So 3 is greater than 2 by 1, so there's going to be a slant asymptote. So we're going to have the third case to apply. So we have a slant asymptote, and we use SA, kind of shorthand for slant asymptote. And this is going to be a diagonal straight line. And in looking for the slant asymptote, okay, so I'm going to be looking at the quotient resulting from taking x squared plus 1 into the polynomial dividend, which we have to be of third degree. And so in looking at what we have in the setup, okay, so with polynomial division, we have applying directly. Now, only constrained by using long division, okay, because the divisor, okay, we have the x term to be x squared as opposed to x. So I cannot get any 0 from x squared plus 1. Okay, and so taking into the dividend, so we have x cubed plus 3x squared plus 4x plus 1. Okay, so just double checking. So we have in the dividends, they have a third degree, second degree, first degree term, and also a constant in x. So there are no missing degree terms in x in the dividend. And now you could set up x squared plus 1 as x squared plus 0x plus 1 just for placeholder purposes. Okay, that is optional. But in the case of the dividend, it is mandatory that you make sure that there are no missing degree terms. All right, so for the first term in the quotient, okay, so we're looking at taking x squared into x to the third, or x to the third divided by x squared, which will be x. And then we have, upon distributing, we have x times x squared becomes x cubed then we have x times 1 is going to be x. Okay, and make sure that that term is situated underneath the corresponding like term from the dividend. So we have x to be a first degree, and so this will be placed underneath the 4x. Okay, and so we can combine terms in the first round of the line division. Okay, so we have, again, with the line division, you're looking at row by row subtracting. So we have x cubed minus x cubed goes out, and then we have, 3x squared is going to remain untouched. Okay, so this is going to be brought down. Again, 3x squared is untouched, so this will be brought down. Again, x cubes canceled. Then we have 4x minus x, leaves us with positive 3x. Then we have plus 1 to bring down. And then for the next go round, okay, so after starting out taking x squared into x cubed, we now have taking x squared into 3x squared. So this is going to be positive 3. And we have, with the next bit of distribution, we have 3 over x squared plus 1 is going to be 3x squared plus 3. And so in looking at what we have in taking the difference between the sets of terms, okay, so we're going to have 3x squared to go out. 3x, again, remains untouched. And we have 1 minus 3 is going to leave negative 2. And I cannot take x squared directly into 3x. Okay, so 3x minus 2 will be the remainder. And again, I'm not concerned about the remainder, just the quotient in terms of what the slant asymptote is going to be. So again, you have the quotient at x plus 3. And so we have for the slant asymptote here, we're going to have that y is equal to x plus 3. Okay, so just summarizing. Okay, so again, for the fraction, there's no real value that will make the fraction equal to 0. Only complex numbers will do this, and we're not working with a complex number system. So x can be anything for the whole rational expression to be defined. So the domain is going to be the set of all real values. And again, since there are no real values excluded from the domain, there is no vertical asymptote. And in terms of any asymptote at all, it is going to be a slant asymptote, whereupon we have that y is equal to x plus 3. And looking at what we have for this particular rational function, okay, so for the image that is going to appear, okay, so we have with the graph. Okay, so for what I have in red, okay, that is going to be the graph of the rational function. And then we have with this straight line that runs diagonally, okay, you're going to have the slant asymptote, whereupon we have y is equal to x plus 3. Notice we have at the extremes, to the extreme left running down, and then to the extreme right running up. Okay, you have a lot of values, okay, upon which the slant asymptote is going to run tangent, okay, to the rational function. But if you notice for the activity in between, especially this part here, you have an intersection. And let me mention, now r of x, just given the right conditions, r of x can possibly touch or even intersect So you can possibly touch, okay, slant asymptotes, and horizontal asymptotes if you have just the right function. But again, R of x never touches vertical asymptotes. Okay, so again, vertical asymptotes are off limits in all cases, but for some cases, the graph of the rational function can, again, come into contact with slant as well as horizontal asymptotes. Okay, now we have in the case of, let's say, just next situation, and we have with our next rational function, so here we're going to have r of x is equal to 2x squared minus 18 all over x squared plus 5x plus 6. Okay, so we have for this rational function, if I'm looking also for the domain and the asymptotes, okay, so we have, again, for x squared plus 5x plus 6, okay, so we have for this expression in x, okay, we are going to have some exclusions from the domain, okay, that are real numbers, unlike what we have with x squared plus 1. And so we have for this trinomial, again, we're going to have the factors to be x plus 3 as well as x plus 2. Neither factor can be equal to 0. So if x plus 3 cannot be 0, we have that x cannot be negative 3. And if x plus 2 cannot be 0, okay, we have that x cannot be negative 2. Okay. So the domain is going to have two exclusions. So we have those values of x, okay, that are less than negative 3. And bypassing negative 3, okay, we have the next set of values x will be those that are greater than negative 3 and less than negative 2. And then we finally have those values of x that will be greater than negative 2. Right. Now, regarding any asymptotes, okay, again, we have two exclusions from the domain. So there could possibly be up to 2 vertical asymptotes. And looking at what we have upon further examination, and this is where the factoring stage for both the numerator and denominator will be carried out completely. Okay. All right. So again, you're looking at the exclusions from the domain before any reduction is performed. Now, looking at factoring, so we have in the numerator, okay, right now, you have two processes here. Now, the greatest common factor between the terms is going to be at 2. And if you notice, okay, we have x squared minus 9, so we have a difference of squares. And then we have for x squared plus 5x plus 6. Yeah, with these factors, again, we have the quantity of x plus 3 times that of x plus 2. And for what we have in the case of factoring, x squared minus 9. So we have the quantity of x minus 3, as well as the quantity of x plus 3. Again, we have all over the quantity of x plus 3 times that of x plus 2. And if you notice between the numerator and denominator, okay, we have a common factor with x plus 3. So we're going to have x plus 3 to cancel completely. X plus 3 cancels out. So this is going to signify that instead of a vertical asymptote, there is going to be a hole at x is equal to negative 3. Then we have for the simplified form, now you could distribute 2 over the quantity of x minus 3, or just leave in factored form. Regardless, okay, we have the denominator factor x plus 2 to remain. And since x plus 2 remains, okay, this means that the restricted value of negative 2 is going to define the only vertical asymptote there is for this rational function. So we'll have a vertical asymptote at x is equal to negative 2. Okay, so you have at least an asymptote that runs vertically. And to see if we have any other type of asymptote, so we have with, once again, this rational function. Okay, so we have 2x squared minus 18 all over x squared plus 5x plus 6. And looking at comparing the degrees. Okay, so in the numerator, the higher order term, we have a 2x squared. And it's from the square of x, okay, that n is equal to 2. And likewise, with the denominator, we have a square of x terms, so we have m is equal to 2. And so for the scenarios that we have, okay, we'll have both n and m are equal to 2, so n is equal to m, and so there's going to be a horizontal asymptote there's going to be a horizontal asymptote, and this will be y is equal to the constant that results from taking the ratio of the highest order terms. So we're looking at y is equal to 2x squared all over x squared. Okay, so we have a vertical asymptote at x equal to negative 2, and we have a hole in the graph at x equal to negative 3, and we have a horizontal asymptote at y is equal to 2. And looking at how this is going to appear. Okay, so we have the graph, let's see, in this case, right, so we have of 2x squared minus 18 over x squared plus 5x plus 6, and we have with the graph, okay, so you have these blue curves, okay, over to the left and over to the right, okay. So r of x is broken up into these two sections. And then for the what looks like a plus sign formation, we have again with the vertical line. That is in reference to the vertical asymptote x is equal to -2, and the horizontal line that is running continuously from end to end, that is the horizontal asymptote, which we have at y is equal to 2. And again, we have a hole in the graph at x is equal to -3. All right. So you have a couple examples here, the first of which has a slant asymptote, and the other which has all of a vertical asymptote, a horizontal asymptote, as well as a hole in the graph. And if I didn't say this before, I have been asked before if you can have both a horizontal asymptote and a slant asymptote, and the answer to that question is no. If it has to be one, it's going to have to be one or the other, but not both. All right. Now, for what we have from the text, okay, we have on page 318, and we have for number 59, okay, and this is going to be kind of a simplified ratio, and we have for this particular setup. So we have with number 59, okay, so you have a function f of x. And this is equal to 4x minus 9. And this is all over x squared minus 9. Again, if we look for the domain, what the exclusions will be, okay, so we have x squared minus 9. Cannot be 0. Okay, so you have, again, so you have x squared minus 9 cannot be 0. Now, so you look at factoring. Okay, so you have the quantity of x plus 3 times that of x minus 3 cannot be 0. Okay, from the factors. Okay, so to keep the denominator from equaling 0, x cannot be -3, nor can it equal 3. And so we're going to have, in the case of the domain, okay, so we're going to have those values x, where x is less than -3, and then we'll have those values x that will be between but not including negative and positive 3. And for the rest of the domain, okay, so you have those values of x which will be greater than 3. Okay. All right, so we have in this setup, we have potentially 2 vertical asymptotes. So just looking at what we have for f of x, again we have 4x minus 9 all over x to the second minus 9, and just looking at the factored form, once again we have x minus 9, we have equal to x plus 3 times x minus 3, and notice we do not have any factors shared between the numerator and denominator. So this is going to be the, so in essence, f of x is already simplified, and this happens to be the simplified form in factored notation. So for what we have in this case, we have both x plus 3 and x minus 3 to remain. And since they both do, it's going to follow that we're going to have both of these restricted values will define the vertical asymptotes. So you have the vertical asymptotes x equal to -3 as well as x is equal to 3. Now for f of x, okay, so you have equal to 4x minus 9 all over x squared minus 9. So in terms of any other type of asymptote, so again, this will come down to degree comparison. So here we have n is equal to 1. And we have the m is equal to 2. And here we have a case of where n is less than m. And if the degree of the numerator is less than what is in the denominator, okay, there's going to be a horizontal asymptote such that y is equal to 0. So the horizontal asymptote is going to be the x-axis. And so looking at what we have among the defined characteristics, okay. All right, so both exclusions from the domain become vertical asymptotes. And again, because the degree of the numerator is less than what is in the denominator, again, you're going to have the x-axis, or y is equal to 0, to be the horizontal asymptote. And so just taking what we have here, and so just making the view larger. And we have zooming in, okay, and just something I do want to point out. Okay, so for these sections in blue, these three sections, you know, to the extreme left, to the extreme right, and also in the middle, okay, you have referencing the rational function 4x minus 9 divided by all of x squared minus 9. And we have with the vertical asymptotes, again, we have x equal to -3, and also we have x is equal to 3. And again, just looking at what appears, okay, these sections of the rational function come very close to touching the vertical asymptotes, but it's going to come very, very, very close, okay, but will never officially come to contact. So the vertical asymptotes are, once again, off limits. Now for the horizontal asymptote, which we're going to have at y is equal to 0. Okay. So once again, throwing in the horizontal asymptote, y is equal to 0. Again, vertical asymptotes are off limits. Now to the extreme left and to the extreme right, okay, now you're going to have the rational function graph to come tangent, okay, to the extreme ends of the horizontal asymptote y is equal to 0. But if you notice, we have the middle section, okay, we have contact, not just contact, but intersecting. So again, this is another case of where the rational function can touch, you know, a slant asymptote as well as a horizontal asymptote. So again, just with this part, okay, so you have contact with horizontal asymptote. All right, now in the case of what we have concerning number 60, okay, And there'll be some level of similarity with number 59. And in the case of number 60, okay, so you have f of x is equal to 5x minus 8 all over x squared minus 4. And for what we have here, okay, now the denominator cannot be 0 in value. Okay, again, we have a difference of squares with x squared minus 4, whereas we had before x squared minus 9. And looking at factoring, so I have the quantity of x plus 2 times that of x minus 2 cannot be equal to 0. Again, we have that x plus 2 and x minus 2 cannot be 0. And so we're going to have excluded will be additive inverse values. So left out, we're going to have negative 2 as well as positive 2. So we have in the case of the domain, okay, so we have those values of x that will be less than negative 2. And you'll have those values of x, okay, between but not including negative and positive 2. And finally, we're going to have those values of x, okay, which will be greater than 2. And looking to see just what asymptotes there are. So here we have 5x minus 8 all over x squared minus 4. And to see whether or not this function is already in simplest form, so we have in factoring the denominator, we have the quantity of x plus 2 times that of x minus 2. And guess what? Just like x plus 3 and x minus 3 moments ago, okay, x plus 2 and x minus 2 are not going to be factors of the numerator. Okay, so you have x plus 2 and x minus 2 remain. And it's going to follow that the vertical asymptotes will be both x equal to negative 2 as well as x is equal to 2. And regarding the degree comparison to see if we have any additional asymptote. So again, we have f of x is equal to 5x minus 8 all over x squared minus 4. So you have in the numerator, okay, so you have the n is equal to 1. And from the denominator, okay, I have the m is equal to 2. And so we're going to have with n at 1 and m at 2, we're going to have the n is less than m. And so there's going to be a horizontal asymptote, once again, at y is equal to 0. All right. So looking at the illustration, right? say y is equal to f of x, okay, is equal to 5x minus 8 over x squared minus 4. So again, you have these three sections defining, okay, what we have for the rational function. And again, we have the vertical asymptotes with x equal to -2 and x equal to 2. Again, the vertical asymptotes are off limits. And once again, if I include the horizontal asymptote, y is equal to 0. Notice again that we're going to have contact between the middle section of the rational function and y is equal to 0. But for all other locations, okay, you're going to have running tangent in fashion. All right. Now, in the case of what we have with numbers 70 and 72, okay, those are going to be simplified ratios, and so the process of attaining the domain as well as the asymptotes will be a quicker, arguably simpler process in comparison to the prior exercises. Now, for what we have in the case of number 70, and we have for this function, okay, this is expressed in the form of g of x is equal to x minus 3 all over x minus 1 Okay, so we have for the domain, okay, so x minus 1 cannot be 0. So we have the x cannot be equal to 1. Okay, and so we're going to have, in the case of the domain, if there is a value x, it's going to be one kind of entity. Either it's going to be a value that is less than 1, or it's going to be a value that is going to be greater than 1. And if you notice, okay, g of x is already simplified, or already in simplest form. So that means here that x minus 1 remains. And from this, okay, since x minus 1 is not going to cancel out, that means that the restricted value is going to form the only vertical asymptote for this rational function. Okay, so we have that x is equal to 1. And again, just for any other asymptote, we have g of x is equal to x minus 3 over x minus 1. And again, both the numerator and denominator will be of first degree. So I have n is equal to 1 as well as m is equal to 1. The values are identical. And if the powers are going to be the same, okay, again, we'll have a horizontal asymptote. And once again, it'll be a non-negligible constant, which will be formed by taking the ratio of the highest order terms in the numerator and denominator. So this, in this case, we have x over x, and this is going to reduce to 1. Okay, so you have a vertical asymptote at x equal to 1, and a horizontal asymptote at y is equal to 1. And just seeing how all of this is going to be laid out. Okay, so just taking a view of what we have here. Okay, so we got the curves once again. Okay, so we have this time in the upper left and lower right hand sections, and again you have the looks like a plus sign, and again we have running vertically, we have the vertical asymptote at x equal to 1, and again running across from end to end we have the horizontal asymptote at y is equal to 1. So that would be the dynamic in terms of how the graph of this rational function is going to be carried out. Now, for what we have in the case of number 72, then we have for this rational function, so this time we have h of x, okay, is equal to 2x minus 4 all over x plus 3. And you're looking for the domain. Again, we have a fraction, and this ratio is already in simplest form. And again, for the ratio to be defined, okay, the denominator cannot be equal to 0. So if x plus 3 cannot be 0, okay, well we have that x cannot be equal to negative 3. So you have for the domain, okay, so you have those values x, okay, such that x is less than negative 3. And then we have for the other half, you're going to have those values of x such that x is greater than negative 3. And again, just for h of x is already simplified. So that means x plus 3 is going to stay around, and so we're going to have the excluded value from the domain, okay, to end up defining the vertical asymptote. So you have the vertical asymptote is going to be at x is equal to negative 3. And in terms of whether we have a slant or horizontal asymptote, again, this comes down to the degree comparison, once again, that we have between the numerator and denominator. Okay, so the higher order terms, we have a first degree. We have n is equal to 1, m is equal to 1. And we have n is equal to m. So here we're going to have a horizontal asymptote. And y is going to be the constant formed by taking the ratio of the higher order terms, which we have as we divide 2x by x. So we're going to end up with y equal to 2. And just taking now what we have and taking a close-up view. Okay, so we have 2x minus 4 all over x plus 3. Okay, and a similar bit of history to repeat. Okay, so you have two curved sections. You have one in the upper left-hand section, the other one in the lower right, okay, at least in comparison to how the asymptotes are situated. And again, we have the line running up and down. We have for x equal to negative 3, and then we have running horizontally Okay, we have the asymptote y is equal to 2. And with the nature of this particular rational function, okay, you're not going to have contact with either of these asymptotes. It's just going to run tangent in fashion. All right. Now, we're going to have a bit of a set of special cases. And we have crossing over to what we have for number 86. Okay, and for number 86, okay, so this time we have a function, and we have u of x. Okay, you don't see the letter u very often. Okay, so you have u of x, and we have is equal to negative 3x squared. All over x squared plus 1. Okay, and you're going to have a bit of history to repeat, especially from the very first example we looked at. So again, we have x squared plus 1 in the denominator. And once again, you cannot factor in real integer coefficients, okay, the sum of squares. So if I isolate x squared and take the relation going from x squared to x, which now cannot be equal to plus or minus the square root of negative 1. You can have the x cannot be plus or minus I. Okay, so again, we have no real values excluded. Only imaginary numbers or complex numbers excluded, and we're not dealing with the complex number system. So that means that, once again, x can be any real value. And also, since no real values are excluded, again, there will be no vertical asymptote. And in terms of whether we have any kind of asymptote, we have in the numerator, okay, we have n is equal to 2. And from the denominator, okay, the higher order term is x squared, so we have m is equal to 2. And again, we have that n is equal to m. Okay, so if n is less than m, or if n is equal to m, there's going to be a horizontal asymptote. In this case, you have y to be the constant that will result from reducing the ratio of the higher or highest degree terms from the numerator and denominator. So you have negative 3x squared all over x squared. And so we're going to have y is equal to negative 3. And so for this particular view, okay, again, there is no vertical asymptote, just the horizontal asymptote, y is equal to negative 3. And for the graph itself, okay, for y is equal to, or u of x is equal to negative 3x squared over x squared plus 1. This looks almost like a bell curve, or what is also referred to as the normal distribution curve in statistics. And again, just where it kind of bottoms out at the extreme left and right, you're going to have to run tangent to the only asymptote this rational function has, and that asymptote being y is equal to negative 3. All right, and then we have for our other special case, and we have for number 90, okay, and we have on this one, have with the function. Okay, so we have f of x is equal to, and we have 4x to the fourth all over x squared plus 8. Again, we have a little bit of history to repeat. Okay, so you have x squared plus 8 cannot be 0, and again, we cannot factor into integer coefficients. And if I isolate x squared, so we have that x squared cannot be negative 8. And just lowering by the square root property of equality. Okay, in this case, we'll have not equal. So x squared goes to x. For negative 8, we have plus or minus. It's square root values. So we have the x cannot be equal to plus or minus the square root of 8 times I. And you don't have to lower, but for what we're going to have excluded, again, are going to be complex terms. Here we have positive and negative 2 times the square root of 2i. So again, we have no real exclusions. And we're going to have, again, this bit of history to repeat. So again, we have the domain. It's going to be the set of all real numbers. You can express with the letter R, or again, parentheses around negative and positive infinity. And again, since there is no real exclusion, there is no vertical asymptote. And again, looking at the degrees in the numerator and denominator. So we have with 4x to the fourth, we have the n is equal to 4, and in the denominator I have the m is equal to 2. And looking at the comparison, so you have 4 is greater than 2. And out of your possible cases here, so you have 4 is greater than 2, and the difference is going to be 2, so you have by more than 1, so you're not going to have a horizontal or slant asymptote. So we had no vertical asymptote to begin with. And once again, we have no slant asymptote and also no horizontal asymptote. But just to kind of show you how this will appear. Okay, so this is what you have for the graph of y is equal to 4x to the fourth over x squared plus 8. Now again, there are no vertical asymptotes. Now, the appearance of the graph, it seems like you might have vertical asymptotes somewhere between, let's say, -3 and +3. But it's just the way this graph is laid out. But what makes this so deceptive is that as the graph is rising, to the extreme left you have proceeding ever so slowly to negative infinity. And then we have at the right, you have very, very, very slowly proceeding out to positive infinity. So there are no constraints with any vertical asymptotes. And likewise, we have at the base, okay, you have like in the central part, look, it appears to run tangent to y is equal to 0. And if we had a horizontal asymptote, much of the graph would be running in proximity to the x-axis, not just this through filament that apparently runs between negative and positive 1. Okay, but you want more activity along the x-axis for even considering that there's going to be a horizontal asymptote. Okay, so this particular function you can say is asymptote free, no vertical, horizontal, or slant asymptotes. All right, now in looking at what we have, I'm going to throw this in. My connection's been kind of shaky, at least in terms of the tablet and the OneNote. But let's say that if we have r of x, okay, is equal to x squared plus 5 all over x plus 1. Now, if I were looking for the domain, okay, so you have x plus 1 cannot be 0. And we have the x cannot be negative 1. So you have in the case of the domain, okay, if x is in the domain, okay, there are one of two categories that x will fall in. Either x will be less than negative 1, or it's going to be greater than negative 1. And r of x is already simplified. So that means that x plus 1 is going to remain. So that means that the exclusion from the domain, okay, that is going to be the vertical asymptote. Again, if the denominator factor does not cancel, we have a vertical asymptote. But if it does cancel, that means instead of a vertical asymptote, there will be a hole. Now, regarding the degree comparison between the numerator and denominator, okay, so we have in the numerator, okay, so the degree is at 2. And for what we have in the denominator, okay, we have from x, okay, we have the m is equal to 1. So we have that n is greater than m by 1 degree. And so we're going to have a slant asymptote. And you're going to have y is equal to the quotient attained from taking x plus 1 into x squared plus 5. And now, just for the polynomial division, now you can go with either approach. Now you can take log division, taking x plus 1 into x squared. Notice we have a missing first order x term. And you can also take synthetic division. Okay, and notice, okay, when we kick things off with the divisor, okay, where we had x squared plus 1. Now again, there was going to be a slant asymptote, but I could not use synthetic division on this one because I had x squared as opposed to x as the highest order term in the divisor. But now with x, okay, to be the highest order term in the divisor, I can use either approach. So if you were to go with log division, x into x squared is going to be x. And then we have distributing, x times x is x squared. And then x times 1 is going to be at x. Then we have subtracting, so we have x squared minus x goes out. And we have 0 minus x, so we have a negative x. And we have plus 5. And then we have x, after taking into x squared, we now have x into negative x, which would be minus 1. And distributing, we have negative x minus 1. And subtract, so negative x and what's going to be plus x cancels. 5 minus negative 1 becomes 6. And I cannot take x directly into 6. So we have the quotient at x minus 1. And I'll just mention, again, I can perform synthetic division. And if you opted for this route, okay, so representing x plus 1, you have the 0 value of negative 1. So in synthetic division terms, so you got negative 1. And for the coefficients of the dividend, so we have 1 for x squared, again 0 for the missing x term of first order, and then we have the number 5. So we have here bringing down 1. So you have negative 1 times 1 is negative 1. And again, with synthetic division, I'm taking column by column addition. So we have 0 plus negative 1 is negative 1. Negative 1 times negative 1 is positive 1. 5 plus 1 is 6. And if you notice, you have in both of these, we have the remainder to be at 6. And for what we have in terms of the quotient itself, we have the 1 and the negative 1 at the front, and the first one will be in reference to 1x. Then we have minus 1. And so we have in both of these scenarios, we have the slant asymptote to be y is equal to x minus 1. And just looking at how all of this is going to appear. Okay, so again we have a, so just bring this over. Okay, so you have a vertical asymptote at x equal to negative 1 and a slant asymptote at y is equal to x minus 1. So these red lines are going to be your asymptotes, and for what I have kind of bowing in and out, okay, we have for these upper right and lower left hand sections, those will be in reference to the rational function x squared plus 5 all over x plus 1, and it's going to turn out that the extreme ends will be running tangentially to those asymptotes. All right, and there is one other item, and this will be crossing over to the next section, and this is going to be what we have with inequality statements. And for this, okay, for this next part, okay, we can take a break from the graphing, okay, for this part, and concerning polynomial inequalities. Okay, and let me just kind of kick things off. Now we've been looking at determining zeros on an intermittent basis, and let's say that let's see, let me do it this way. Let's say if you're looking at determine So if you're looking at determining the values of x, for the following. Okay. Now essentially we'll be looking at kind of displaying 5 problems and compacting into one. And I'll show you what I mean. Say if you have a statement x squared minus 4 is equal to 0. Okay, so we've seen that plenty of times. But let's say if you're crossing over to the inequality realm, say if we have x squared minus 4 is less than 0, and we have x squared minus 4 is less than or equal to 0, and we have x squared minus 4 is greater than 0, and we have x squared minus 4 is greater than or equal to 0. Okay, so I'm going to form a bit of a table and sort of categorize, okay, what's going to be transpiring, okay, among the inequalities. And I'm going to use just the equation here, where we have x squared minus 4 is equal to 0. So just taking what we have in the first instance. So I have x squared minus 4 is equal to 0. And again, you can use the square root property of equality, but I'm just going to factor. Okay. So taking the factors and setting equal to 0. So I'm not looking at exclusions from the domain anymore. I'm looking at what will make this expression equal to 0. So we have 2 values, okay, whereupon we're going to have negative 2 as well as positive 2. Okay, so we have, so in this case, we have x equal to negative 2 as well as x is equal to 2. So we have with the zeros, you have your 0 values, okay, which will be negative and positive 2. And again, so for x squared minus 4 is equal to 0, we have 2 values, x, that will make this true, so you have negative and positive 2. Now, in terms of setting things up for the inequalities, okay, I'm going to use these zeros. And set up a table, okay, with intervals for the column headings. So think of like working with the whole real number system. And what I'm going to do here is that I'm going to start from negative infinity and approach, but not include the smaller of the zeros. And the next, okay, I'm going to have running between, but not including, negative and positive 2. And then for the rest, I have those values of x which will be greater than 2. Okay, so we're going to set up intervals, okay, going from negative to positive infinity. And again, you have kind of rank order, or the zeros we have, and just be exclusive of these for now. Okay, so just separating. Okay, so we have kind of divide up. And after separating, the interval sections. Okay, what I'm going to do is kind of probing each of the subinterval sections. And we have like a tested value input, and just call this tested value x. And what I mean by this, okay, it's like I can pick a number that is less than -2. So this would be something that is more highly negative than -2. So let's say something like -4 would be a possibility. And if I go with a value between but not including negative or +2, like I could choose -1 or 0 or 1. And we go with 0 on this one. And then to test out any value x greater than 2, we can pick any number greater than 2, and we'll go with the number 3. It doesn't have to be just those numbers, but as long as those numbers belong to the subinterval section or the category that is immediately above. And again, we have throughout, okay, for the comparison to 0, okay, again, you have the binomial expression, x squared minus 4. So again, we have f of x is equal to x squared minus 4. And if I test out the value of the function for these inputs, okay, so we have for f of -4, and we're just about there. Okay, so you have -4 squared is going to be 16 minus 4, and that is going to be at +12. And for f of 0, we're going to have 0 squared minus 4, and that is going to be equal to -4. And for f of 3, okay, so we have 3 squared minus 4. Okay, so 3 squared is 9 minus 4, and the difference is going to be a +5. Okay, and in the case of what we have for the sign of f of x, okay, so we have, first of all, okay, so anything you plug in less than -2, the function output is going to be positive. So we have f of x is going to be greater than 0. Anything that is greater than -2 but less than 2, okay, your output is going to be negative. So you have the f of x is less than 0, and if the input is greater than 2, the output is going to be positive. So you're going to have f of x is greater than 0. Okay. So just kind of categorizing what we have here. So we got with these items. So for x squared minus 4, let's kind of branch out here. We're kind of pressed for time. Okay, but where x squared minus 4 is going to be less than 0, you're referencing where f of x is less than 0. So in the case of the solution, okay, so where x squared minus 4 is less than 0, so you have the solution is going to be with the subinterval that is up above, so you have between negative and +2. Now for less than or equal to 0, we're going to have for that solution, you're going to have negative and +2, and thanks to the equal sign, you're going to have negative and +2 in the brackets. Now where we had to be greater than as well as greater than or equal to 0, your solution set, between -infinity and -2. Now again with greater than, you have over here and also at the end. And where we have greater than or equal to 0, those values negative and positive 2 are going to be in the bracket. Okay, so for the first part, okay, we had negative and positive 2, and then for less than or equal to, greater than or equal to, I'm adopting from these sections above. Less than 0, got this part. Equal to 0, I'm including the zeros. Greater than, I got the first and last subinterval sections. And with equal, we have the negative and the positive 2 in the brackets.